a2 of x, right? And now I've got the second derivative of y1 plus y2. That's just y1 double prime plus y2 double prime. Just go into this equation and replace y by y1 plus y2, right? And then I get a2 of x times what? The derivative of y1 plus y2, which we know is y1 prime plus y2 prime. Plus finally, a naught of x times the sum y1 plus y2 of x. Okay? And I think you can see, okay, just multiply out. What do you get? a2 of x, y double prime, a2 of x, y1 prime, a naught of x, y1. So that's L operating on y1. And then we do all the stuff with y2. What do you get? a2 of x, y2 double prime, a2 of x, y2 prime, a naught of x, y2. That's just L operating on y2. So that checks. Right? Okay. Let's do the second one, okay? We should probably do that one in your head, right? What's L operating on alpha y of x? Okay, just go to the definition. Every place you see y, replace it by alpha y. So you can have a2 of x. Now you can have alpha of y of x, second derivative, plus a1 of x times the first derivative of alpha y, which is alpha y prime, right? Plus a naught of x times alpha y of x. So L operating on alpha y of x. You see, what happens is that the alpha scales out of everything, right? Just pull out the alpha, it's a constant. So you have alpha, and when you scale out the alpha, what do you have? a2 of x, y double prime, a2 of x, y prime, a2 of x, y. Precisely L on y. Okay? So it satisfies that condition. Okay? So you have basically two ways, at least that, for these simple things we concern this course, of saying if an equation is linear or not. You can see if it falls into this form, okay, which again, in words, is just a linear combination of y's derivative multiplied by functions of x, or you can apply this definition over here, okay, and do it that way. So let's go to back to our nonlinear pendulum again, right? That was the second root of theta with respect to time plus g over L sine theta is equal to 0. And again, don't get confused with the symbols. Here the independent variable is x, and the dependent variable is y. Here the independent variable is time, and the dependent variable is theta. Okay? Now, remember, this is a definition of linear operator. So for an operator L to be linear, both of these conditions have to be satisfied. If either one or both are violated, it's not linear. Okay? The simplest thing over here is I'm going to show that condition 2 is now violated. Okay? So, L on theta is just the left-hand side, right? Theta double dot plus g over L sine theta. Okay? Let's do L operating on alpha theta of t. If it's linear, it should be alpha L on theta, right? I think you'll see where we get into trouble now, right? L operating on alpha theta of t is equal to the second derivative with respect to time of alpha theta of t. Okay, that's okay. Plus g over L, the sine of alpha times theta of t. Or alpha theta double dot. Right? So good, I got that part. Oh, not alpha theta. Yeah, alpha theta double dot. Plus now, here's the problem. I've got g over L sine of alpha theta. To be linear, what happens? The alpha has to factor out. And everybody knows that the sine of alpha theta is not alpha sine theta. Right? Sine of 2 theta, remember? From your high school trig? 2 sine cosine. Okay? And therefore, nonlinear. Okay? Because it violates condition 2, and you can show that it violates condition 1 also. In that case, when you do L operating on theta 1 plus theta 2, you'll end up with the sine of theta 1 plus theta 2, which you of course know is not sine theta 1 plus sine theta 2. Okay? So this is again something which I want you to get used to. Okay? All I will do is that, for the first few weeks, I'll probably write out this expanded form, and I'll put down on the bottom L on y. After a while, I'm just going to drop it, okay? And it'll be second nature to you. Oh, I know what he means by L on y. It's just this guy over here. It just makes writing things easier. And also, many times when you generalize stuff, It actually makes it clearer, okay, because you're not obfuscated by all types of details that really aren't important. Okay. So any questions on that? Okay. So that's basically your definition of your linear operator. Okay. Okay, another thing which we basically, again, when we come up with a rigorous definition is, what do you mean when you have a solution to a differential equation? It's almost kind of, I don't even have to write this down. It means basically, if you can come up with a solution and you plug it back in, it reduces it to an identity, right? Just when I solve a quadratic, x squared plus 5x plus 6 equals 0, and I use the quadratic formula, factor it, I get the roots. Right, so you plug those roots back in, 0 equals 0. Okay. But there's one little subtlety that's very important that will become clear as we go through the course. In the definition, that definition is almost perfect, I say 95% perfect, but there's one little condition that is missing. So let me just write it down over here, okay? This is, let's put it this way. If y equals p of x is a solution, okay, I'm defining solution to an ODE now. Solution. And then this applies even to the most general one that we did. Say f of x, y prime. Remember we did the most general one? Y super n of x from the last time. This is just some hideous non-linear equation in general, depending upon the independent variable x, y, and its derivatives up to order n. So if that's a solution, then it means when you plug in for y phi of x, you satisfy it identically. So that means that f of x, phi of x, phi prime of x, down to phi of x, I guess, n derivative, is identically 0 on some interval. Here's something which is a little twist. On some interval. And we see examples of this, so it's not too abstract yet anymore. What will happen is that, see, when you had a simple thing like a quadratic equation, or even a cubic, you get the roots. Okay, the roots are x equals 3, 5, and 8. That's it. Nothing else has to be said, right? You got the roots. That's it. When you have a differential equation, you'll notice basically that the function y is much more different than a root to a polynomial equation, right? This function y has to be differentiable, right? And it has to basically satisfy the equation. What we'll find is that many times we'll get a solution to a differential equation, but it'll be valid only on a certain interval, like maybe between minus 1 and plus 1. And outside that interval, it doesn't make any sense, or it blows up. Okay? And that's always a reflection of some physical characteristic of the system that you're modeling. Okay? So remember, whenever someone kind of second thought, anytime someone tells you or you think of a solution to a differential equation, attach to that on some interval. Okay? Okay? So in fact, they say I have a solution is really kind of incomplete. Is it valid for all values of x, or only certain values of x? And we'll see plenty of examples today where this will enforce that. You have to remember that it's always a solution on some interval, not necessarily all values of x. Okay. Okay, now to that end, what we're going to do, this is, again, we still haven't talked about solving equations, but remember I told you, I think the first day, that an advantage of a course like this is that you can always check your answer, right? Where suppose you have a problem you want to solve a differential equation, you shouldn't come away and say, I don't know if I got the right answer or not. Because you can just plug it in and see if it works, right? Just like when you solve a quadratic, right? You can always just check the roots again. So, what we're going to do now is just, these are things are just elementary about verifying solution, okay? Now, in presenting this, I'm going to write down a differential equation. I'm just going to give you the solution to the equation. I don't expect you at this point to be able to derive that, right? That's the whole purpose of the course. But you should be able to, at this point, at least verify that that's a solution, okay? And again, this is not just an academic exercise, because later on, when you'll actually be solving the equation, I'm not giving you the solution, but you have to derive it yourself. You want to be able to check it, okay? And this is very straightforward. Let's give an example over here. So I'll put it like this. I'll say claim y equals 1/16 x to the 4 is of x is a solution and the solution, okay, or the unique solution. Because what happens then is we find out, wait, there's some arbitrary constant in there. It's a first order equation, right? And clearly it's not going to be the most general solution. So when I say a solution, I'm saying basically that's not the most general, but I claim that it is a solution to the equation. Now, okay, I didn't derive it, okay, but can we at least verify that it's a solution? Sure, just plug it in, okay? So you have your answer then, okay? So from this it follows that dy dx, okay, the root of x to the fourth is 4x cubed, so you get 1/4 x cubed. Okay, plug that into the left, plug it in, plug it to the right, and see what happens. So now we have, plug into the equation, we have 1/4 x cubed, I'll put in the question mark, that's the left-hand side, x radical y. Well, what's the square root of y? Remember, it's a positive square root, so it's 1/4 x squared. And clearly the right-hand side is 1/4 x cubed, yes. And there's no restriction on that, so that's valid for all values of x, right? So what we can say is that even though we didn't derive that solution, yes, I can say with confidence that 1/16 x to the fourth is a solution of this differential equation and is valid for all values of x. Okay. And some of the homework exercises just, emphasize this. And again, if you find out that when you're doing this thing, you forgot how to differentiate things like sines and cosines, okay, review your calculus, okay, because I'm not going to be going over that kind of stuff. Okay. Here's another one. Plane. Y equals x dx is, again, a solution to y double prime, or the second y respect to x, minus 2y prime plus y equals 0. Okay? Okay, so I'm saying basically, I claim that the function x e dx is a solution to y double prime minus 2y prime plus y equals 0. Question? What? Yes?
Why did you take the x out?
Why did I take what?
X. It's 1/4. X is the cube prime.
Oh, because when I differentiate x to the fourth, it's 4x cubed. 4/16 is 1/4.
No, I know.
Yep.
If 1/4 is equal x cube, right? Then you
Yeah. In other words, I want to verify that it solves, right? So on the left-hand side, I need dy dx. I just calculated dy dx. It's 1/4 x cubed. And on the right, in other words, what you do to verify a solution is you take the solution and its derivatives and you plug it into the given equation, in the original equation. Here's the equation that we're trying to verify that it solves. So for dy dx, I have 1/4 x cubed. The right-hand side, I need x times the square root of y. Okay, what's the square root of y? Just take the square root of it. Okay. Okay, so now we have another equation. Again, we'll just, x e dx is a solution of that guy. Minus 2y prime plus y equals 0. Okay? If indeed it's a solution, again, we can see x e dx is well behaved every place, right? So it's a solution for all values of x. Is it the most general solution? No. Okay? Matter of fact, there should be two arbitrary constants in there to get the most general solution. This happens to be just one of those special, solutions over here. Well, again, let's verify it at least. Okay? Well, what's dy dx? Since they were kind enough to give you the answer, I just differentiate, use the product rule. I get x, the derivative e dx is e dx, plus 1 e dx. That becomes e dx, parentheses, x plus 1. Okay? And just as like a general rule of thumb over here, always try to simplify things if you can. Okay? It just makes the algebra easier. Okay? So I've seen students do stuff like that, and that thing grows and grows and grows, right? It's obvious that's just e dx plus 1. Now we're going to crank out one more derivative. Okay? That's easy enough. Second y with respect to x. And again, I'm using the product rule here, and if you don't know the product rule, you forgot it, your responsibility to go back and review it. Okay? Use the product rule again. The derivative of e dx is e dx times x plus 1 plus e dx times the derivative of x plus 1, which is 1. And we find that we get e to the x, parentheses, x plus 2. Okay? X e dx and then 2 e dx is just that. Okay. to the notation now. L operating on Y. What do you mean L on Y? The left-hand side. Okay? So see how you see that? This way I don't have to write down Y double prime minus 2Y prime plus Y equals 0. L on Y, left-hand side. Well, let's take all our derivatives and plug them in. The first term in the differential equation is a Y double prime. Okay, we just calculated e dx x plus 2. Okay? Minus 2 times, now I need the first derivative. Let's write in that line. E dx x plus 1. Okay, finally, plus y, okay, x e dx. Okay, this better go to 0. We'll see. L operating on y equals, let me factor out an e dx. Here I got an x plus 2. Factor out an e dx over here, I get a minus 2x minus 2. Factor e dx over here, I get a plus x. If I didn't make a mistake, it is 0, right? X and x is 2x, cancels with 2x. 2 minus 2 is 0. So it checks. Okay? So all we've done is just verify that the function x e dx is a solution to the equation. Again, the whole purpose of this course is not just to get solutions and plug them in. Okay? How do you solve this if I didn't give you the answer? Right? That's the whole idea of the course. Okay? But again, this thing of just being able to verify is very, very important. Okay? Because you'll catch a lot of mistakes that way. Now we're going to talk about implicit solutions to differential equations. So far, the two examples which I gave you, in the first case I said y equals x e dx, and in the first case I told you y was 1/16 x to the 4th, and that's the most desirable form of a solution to a differential equation. You want to be able to basically write the dependent variable explicitly as a function of the independent variable. It comes out that in many cases you can't do that. You get what's called an implicit relationship between x and y. Okay? And it would be very hard to solve the thing explicitly.